Okay, well, let's see. Let's go ahead and get rolling. It looks like I'm on the air. So what I was going to go through today is part of the our hands-on example number 4. I'm not going to go through the entire thing today. What I was going to focus on today is to look at the to look at the component Pascal component. In other words, we're going to go ahead and build the component Pascal function that's based upon the BUGS model library, and also illustrate to you how you can go about testing those sorts of functions once you write them. So let's go ahead and dig in. Let's first of all remind you about what the example is. Let's see, I want to go ahead and pull this up full screen. That's what I was looking for. Okay, so just remind you, so we're going to be doing it's a PK/PD modeling exercise. We're going to be looking at neutropenia induced by our drug here, ME2, and we're going to focus just on modeling the data from the phase 1 multiple dose study, which was a parallel dose escalation design involving multiple doses of our drug ME2. There were 8 subjects per dose arm, and we have, 6 dose arms here, placebo and several doses up to 80 milligrams given twice a day for 7 days. We've got a fairly dense sampling schedule here for the PK. We have to worry about our limit of quantitation here, so we've got to deal with our left censoring. And then finally, our pharmacodynamic model here, our pharmacodynamic data, are the absolute neutrophil counts, which you'll see abbreviated as ANC, and that's just measured daily over 12 days. We've got a few possible patient covariates. As I recall, the only one I've got set up to use right now is just body weight on clearance and volume, just like we had done when we did the population PK modeling that included this. This is actually the PK data here is actually a subset of the data that we used in the population PK example. So the data here, again, this is the same data on the left-hand side that you saw before. Got some dense sampling on day 1 and on the last day, and then some troughs in between. And then we've got our neutrophil counts on the right-hand side, and here they're plotted as time courses also. So we've got our absolute neutrophil count on the y-axis, time on the x, and then each panel is a different dose arm. And in particular, when you take a look at the higher dose arms, particularly the 40 and the 80 milligram, you can see the sort of general downward trend in neutrophil counts over time here. And that's the thing that we want to model. The model we're using is one described by Freiberg and Carlson. So we've got our semi-mechanistic model where we've got a bunch of parameters in here, but just remind you, we've got our proliferative compartment here, which is kind of where our whole life cycle for our neutrophils begins. Then you have a maturation process that is described here as a catenary sequence of compartments. Right here, in this case, we're just going to do 3. That's actually an adjustable thing. You could change this to more or less, but we're going to use 3 here. And then finally, that leads to the thing that we're interested in modeling, because it's the thing we're measuring, which is the circulating neutrophil count. So that's what's represented by the CIRC. In addition, we've got the rate at which our basal cells here are being produced here is actually proportional to the amount in there, and that's described by this little circular component here. And there's a rate constant associated with that. There's also a feedback such that as the circulating neutrophil count drops, the rate at which the new neutrophils are formed is increasing, but it's done back here at the beginning, so it happens way back at the beginning of the life cycle. So any feedback that happens here, there's a delay associated with it because of this sequence of transit compartments. And then the way we're actually going to parameterize this is, instead of parameterizing it directly in terms of these individual rate constants here, we're we're going to parameterize it in terms of a mean transit time across these compartments. And then the various k's will be derived from that mean transit time. What else am I missing? Well, I guess I didn't mention, of course, at the end there's a loss. Our neutrophils don't live on forever. They eventually die off, so that's described as a first order process here. And finally, the drug effect is described as influencing our proliferation back here. So that's where the drug effect's going to come in. And then when we describe that in terms of a set of differential equations, we have that here. The easiest part to describe is the stuff in the middle here. So basically this components here is our sequence of transit compartments finally going out to the last compartment. So you've got the rate of change in the amount in each one of the transit compartments, as well as our final circulating neutrophil compartment here. And those all look more or less the same. They're all fairly simple linear compartmental transfers here, with basically one component describing the rate of input into that compartment and one describing the rate of exit. All of them just proportional to the corresponding compartments. So going back to the picture then, that's basically describing the process out here, dealing with those. And then and I guess what isn't evident is this feedback here does not describe a rate process here. So this arrow coming out of the the circ compartment here doesn't represent a loss from the circ. The only loss is down here. Let's see here, what else to tell you. Okay, so that's the easy part here. The more complicated part is what's going on at the beginning here when we're talking about our proliferative compartment here. So the rate of change of the cells in that compartment then is more complicated. The loss is simple. That's just a simple first order loss component, but the rate at which new cells are being formed here is a bit more complicated. In the absence of drug, it would be simple. It would just be K-prol times prol here. But in the presence of drug and the feedback processes here, it gets more complicated. We have a drug effect here described as 1 minus E drug. So in other words, the E drug is written such that the drug effect as E drug goes up, this term goes down, and therefore the rate at which those cells are proliferating goes down. And that's describing then our myelosuppression process. And then the other component here, where we've got our circ0 over circ raised to a power gamma, that component then is describing that feedback process that tends to maintain the number of circulating neutrophils are at a certain level, or at least it attempts to keep it at a certain level. And then finally, for our drug effect, we're going to do that using probably almost the simplest model possible here. I guess the simplest might be just an on and off, but we'll have it as just a linear model in this case. So it's just E drug is just proportional to the drug predicted plasma concentration of our drug. So alpha then is a parameter characterizing that effect. We are making the assumption here that our rate constants are all equal here. The K-prol, K-circ, and KTR are all going to be the same, and I'll refer to them in terms of KTR when we actually code this out. And in addition, what we're going to do is we're going to parameterize this thing in terms of this mean transit time, and that relates to our KTR according to this relationship. So it's N here represents the number of transit compartments. So in this case, that's 3, the transit 1, 2, and 3. So it's going to be N plus 1 over KTR. The plus 1 comes from the fact that though we have 3 sort of intermediate compartments, we have a final transfer step at the end. So it's really a count of all these transfer steps leading to the circulatory neutrophils. So that's what we're going to be coding. Let's see here. For the PD component, remind you again that the put in red here, any parameters in red are what I term system parameters, which are, I intend that to mean that they are drug independent in here. They just depend upon our physiologic system. And so if we have information for those parameters based upon previous work, either just straight physiologic experiments or perhaps past experiments on other drugs that cause myelosuppression, the conceptualization of the model is such that we think those numbers should stay the same from drug to drug, so we can use that information from those past experiments to influence our analysis. And of course we're in a Bayesian framework here, so we would do that by specifying those as informative prior distributions. The PK model is going to be the same one we used before, which was the conventional linear two-compartment model with first-order absorption. Let's see. Actually, for today, I don't even need to worry about this part because we're not going to implement anything related to the variability in any of these components, since we're just going to be working with what amounts to a deterministic model to describe the results for an individual in here today, because we're just going to look at our component Pascal model today. So we'll deal with the rest of this next time. Ditto for any of the values here. We're not going to deal with those today. Those all sort of get dealt with when we finally write our final BUGS model and the R script. And so let's go to it. Let me actually leave this up here so we can come back to it. So we can sort of flip back and forth. Let's go to Windows World here and actually look at how we're going to do this. Hopefully you've seen this morning I sent an email because I realized that what I had given you before was, let's see, this file right here, which is called 2CPT NEUT1 model RK45. That one was actually based on some previous things I had done where I had used an Emacs model for the drug effect, and of course in the model specification here I said no, we're just going to do a linear drug effect. So I subsequently posted this morning the appropriate code for the linear effect. In this case, it's actually a fairly small change from that original one. But let's go ahead and take a look at it. And let me fire up our BUGS WinBUGS here, or black box WinBUGS, that is. Let me pull that in there. So this is the 2CPT NEUT2 model RK45. Let's go ahead and make things a bit bigger here. Okay, so this is the model that we're building here. For this part, for now, I've written it in terms of using the Runge-Kutta method, but the things we'll be talking about today are readily transferred to the LSODA method, and I'd actually encourage you to explore both of them. But the core things, the things that you actually need to write to make use of one or the other, are actually identical. So first of all, one of the first things again, that if you were using, say, that effect compartment template that's provided with BUGSModelLibrary, one of the first things you need to do is change the name of the file and change the names that appear at the top and the bottom here, so to be correct. So I've got that changed. The next thing is how many differential equations we have, and so let's go back and look. If we count them up, what have we got? Well, we've got 1, 2, 3, 4, 5 differential equations for the PD component of the model, and our PK component is our 2-compartment plus an absorption compartment, so we've got 3 there, so we have a total of 8. So that's what I've got coded here. And we scroll down to the user derivatives procedure right here. So we've got to change the contents of that. And in particular, we need to write out our differential equations, and that's what's going on in this segment of code right here. And first thing to mention is I mentioned this trick the last time, but I'm using it extensively here. And the trick is the one that I use for the case where we have some non-zero baseline value for the amounts in the compartments. So I need to provide initial conditions for each of those compartments where it is non-zero, and the trick that I prefer to use here is to actually write the differential equations in terms of the change from baseline rather than in terms of the amount in the compartment itself. And when I do that, it's a fairly simple thing to it's a fairly simple way to modify it, and it allows you to easily model the baseline values and pass those baseline values as parameters into this. So that's the first trick we're going to be doing. So let me actually step back again here. So if you look at the nature of this model, there is of course some baseline value that we're going to be working with. Notice that in here the key baseline value that's mentioned is circ0 that shows up here on top. So that is then is going to be a parameter. Again, and notice it's in red, so it's one we're going to treat as a drug-independent parameter. It's something that's a property of our physiologic system, and in particular it would be a property of within a single patient. So it's probably something we'll put some interpatient variation on. So that's our baseline value for the circulating quantity. But now if you actually work through the algebra for the case where we've made this assumption, where all of these three rate constants are equal, what you find when you do that, so in other words, if I ask the question, okay, well then if I've got a particular baseline value for the circulating quantity, the quantity in this last compartment, and I'm at steady state in the case where I've not yet administered the drug, what you'll find is then that the amounts in each of these compartments equals circ0. So that cascades all the way through the model in this case under this assumption that all the rate constants are equal. So that means for all 5 of these compartments, then I'm going to be treating the baseline as equal to that circ0 value. And you'll see the comment in here that for the compartments that are going to correspond to those are going to be the ones where the amount in those compartments is x3, x4, x5, x6, and x7. So that's those 5 compartments. And so I'm going to describe those all in terms of change from baseline, or as I said here, as difference from the circ0 value here. So you start out by writing out your differential equations. Sorry for jumping back and forth. That might drive you a little crazy. But so we start out with these differential equations written in terms of the amounts here, the prol, transit 1, 2, 3, and circ. But then we say, okay, well, let's do a change of variable. For each one of those, create a new variable. Call it whatever you want. In this case, we'll just use the names like in the code where it's like x3, x4, x5, x6, and x7. And those values will equal the original quantity here minus circ0. Well, when you take the derivative of that with respect to that new variable, you actually get exactly the same value because you're taking the derivative of a function of time minus a constant. So you actually get the same derivative value back, but on the right hand side, wherever you see a particular value, you have to replace it by like your corresponding x minus circ0. So wherever you see PROL, you would need to replace that by what did I say, x3 minus circ0. Wherever you see transit 1, you replace that by x4 minus circ0, and so on within the code. Oops. So that's what's kind of going on right here. So, and you can see that noted as a comment right here, is that those are all differences. In addition, to try and improve readability a little bit, you'll notice I've actually written these back out in terms of the names that we were just using. So I've got PROL equals x3 plus circ0, transit 1 is x4 plus circ0, and so on down to circ equals x7 plus circ0. So I've done that so that when I actually write out the differential equations, they look pretty much like we just saw on that previous page. And in fact, those are all right here. So you can see the only thing that might look slightly different is because of the way I've written it. First of all, any place where you had kprol or what was the other one, kcirc, wherever you saw those have been replaced by ktr. And in the first equation right here, I kind of collected up the terms a little bit here, because if we go back again, you can see this is written as kprol times prol on this side, and on this side it's ktr times prol. But under the assumption where kprol equals ktr, you end up with those two terms are equal, and so I just pulled that all off to the left and multiplied it by the remaining terms, and that's why down here you see it written then as ktr times prol multiplying. On the right hand side you can see the 1 minus e drug times circ0 over circ raised to the gamma, and here notice again there's no we don't have a built-in operator for that exponentiation, but we do have a function called math.power. So that's what I've used to do the exponentiation right there. And finally, that whole mess is you subtract 1 from it. Again, the rest of these look pretty much the same as what they look like on the previous slide. So that pretty well takes care of our PD component, and the reason why I sort of these all start from x3 is because we've got 3 other compartments we need to deal with, namely our pharmacokinetics, and that's what's going on right up here. So you can see we've got where we got the usual, and again, reminder, component Pascal, all the vectors begin at 0. So for our first compartment, it's actually got indexed by 0. So the rate of change of the amount of drug in the absorption compartment is just minus Ka times x0. You've got your central compartment, so you've got your rate of change in that compartment is Ka times x0. And then you've minus the sum of our exit rate constants, K10 plus K12 times x1, and then finally plus a K21 x2 for the return from the peripheral. And then finally the mass balance here then for our peripheral compartment. Now if we go back again, look at our differential equations here, notice the E drug term here was written in terms of plasma concentration of the parent drug as opposed to an amount. So inside here, where'd it go? I go ahead and calculate the concentration. I put it in terms of the units that we were originally using. So as I recall, our plasma concentration units, I believe, were nanograms per mil. In here, or I guess equivalently micrograms per liter, whereas our parameters volumes are in terms of liters, our clearances are in terms of liters per hour. So to get the right units here, if I want to use nanograms per mil, I have to multiply by 1,000, and then we've got our amount. Oops, no, I just did a dragging something around here. Okay, here we go. So we've got our amount in the central compartment divided by the volume of the central compartment. In this case, I guess I was using the non-mem conventions of calling the central compartment volume V2. And our e-drug value here, again, that's just our, we just take e-drug is just going to equal some parameter here that I called alpha times our plasma concentration. So that finally ties our PK into our PD in our model. So we've taken care of both our PK calculations and our PD calculations in here. Now this is writing out our differential equations in terms of various names I've given things, and that process of giving names to things all occurs up on top here. So we've got our, you've seen this before, where here the actual argument that gets passed to this user derivatives function is a vector called theta containing all of our parameters, and here I've just given name assignments associating with the various parameters in the theta vector to names that are more recognizable to us. So you've got our various PK parameters right here. And I've got, what else have we got? We've got our, oh, remember I said we were going to parameterize this in terms of mean transit time. So I've got my MTT here, our baseline value for our neutrophils. Let's see, what was gamma was that exponent associated with the feedback. Alpha is our parameter, our slope associated with our drug effect. This again, the assert statement is actually not required, but it's just a way to catch possible errors in passing of parameter values. Let's see, and then some derived parameters. I get my various rate constants here from our clearances and volumes, and finally, I convert from my MTT to KTR. Again, it's that n plus 1, where n being the number of transit compartments over MTT gives us KTR in here, which is what you saw used in, whoops, boy, that flew by too fast. There we go, where you see KTR being used throughout all of our differential equations down here. So that's almost all of the story in terms of the differential equations. I guess I didn't mention it as before, where you have to declare all of the parameters that you use in here, all of the names you're using. And then the other part the user has to do is this annoying little bit down here where you have to count up a few things. So in this case, we have to count up the number of parameters. Well, if we look up here, the number of parameters that we're using directly here is right here. You can see it goes from 0 to 8, so that would be 9 parameters right there. We have 8 differential equations, and associated with each one of those, we have an F and a T lag. So you've got 16 there, so you've got, what did I say, 9 basic parameters, and then you've got those additional ones, 16 of those, so you've got 25. So assuming I did this right, that should say 25 here. It does. The last of the parameters I had listed up above had an index of 8, so it probably makes sense to make the F parameter then the next one in line, which I did, so that would be 9. Then you add 8 to that, and you get the index for the first of the lag times, so that's there. And again, I tell it how many compartments, which is 8. So that's all the parts that you need to change in here. So at this point, if you think you got it, then the next step in here is just to go ahead and compile it. So you go ahead and go to DEV over here, compile and unload. You do that, and if everything worked out well, you get this little OK on the bottom. So we're all set there. And then, as before, we have to also go in and create our WBDev component here of the same name. So we go down and we go down to the WBDev folder here, go into mod, and we have to create one. I believe I already have it here for this particular example. Where did it go? There's a Newt 1. Where's my Newt 2? Maybe I don't have it. I thought I had actually done the example, which meant it had... Maybe not. Well, that's curious. I would have sworn it was there. Okay, am I actually in the right directory, though? Black box WinBUGS. Yep. Okay, well, let's make one. Okay, so the typical thing would be then to go grab, pretty much any one of these things that was associated with the BUGSModelLibrary. I guess to save the amount of editing we're going to do, let's just grab the one that's most closely named to it, which is our 2CPT Newt 1 model RK45. Why don't I just go ahead and replicate that one? Let's do that. Okay, copy of, and let's rename it. In this case, all I got to do is change that to a 2 and get rid of the copy of. I'm still throwing me here. I would have sworn I did this example. Maybe I did that. Oh, you know what? I'll bet I did it on the other computer. Okay. Anyway, there it is. So let's go ahead and grab that and pull it into our black box thing here. Again, let's make it big enough to read. I won't even monkey with the rest of it because the only thing we need to change... Oh, apparently I did change it inside. I just forgot to change the name on the outside. Okay. It's already been changed, but basically all I would need to do is any place here. This should have actually had 1s here. It's already got 2s. Anyway, you just have to change those to be the corresponding name and then go ahead and compile it, which I will do. Okay, compile and unload. Everything's all right. It says okay. And then finally you need to go in to, let's see, go up here to, oh, wrong thing. Go up to the R inside the WBDev RSRC folder. Grab the functions.odc file. Okay, and we have to create one, and in this case it's already created. Okay, that explains why all these work. In this case it's already created, but you would need to create a line just like the one here. And typically I would do that by grabbing one of the other lines, copying it, and then changing the names appropriately. And in this case it's just a text file. You don't need to you do not compile this. Okay, so we've got all of our pieces in here. So in theory, we've got a BUGS function that's appropriate for simulating values from this neutropenia model. Now, when I deal with things like this that are somewhat complicated, I usually don't immediately go and try to analyze a big set of data with it in hopes that it's going to work. One of the first things I often do is write a very simple BUGS model just to make sure the function runs and appears to be producing the correct values given some set of parameters. So let's show you what that process looks like. Okay, let's shrink these back down here. Now again, just a reminder, these functions, when you make a new function like this, it's actually not available to you in the black box session that you compiled it in currently. You actually have to open a new session. So usually then I would close out of a session like this. What didn't I save? Let's see. Okay, I guess I need to save that. I think so. Okay, so we've got that, and let's go over here. I'm going to open up a session again, And the other file that I posted for you is this one here called test2cpt neut2 model RK45. It's just a plain text file that contains a very simple, or relatively simple anyway, BUGS model. It's actually a BUGS model that doesn't even have any random components in it. Let's open it up. Let's see. Do I need... Yeah, let's unwrap it here. Okay. So let me show you what I've done here. Actually, if we go down to the bottom, what you'll see is I just went ahead and instead of down here where I would normally put prior distributions, in fact, I probably shouldn't even have that name here. Instead, what I did, in fact, I can see what I did here. I actually used an existing model here. I probably shouldn't even call these. I get rid of the words here, prior distributions and weekly. These are not weekly informative priors. In fact, these are fixed values right now. So I just put fixed values in for everything. So I've got a set. They might be arbitrary. In this case, I happen to know that these are approximately the values that were used to simulate this data, since it's actually not real data, it's simulated. But they would be just a set of what you think are plausible values that you're going to use to just test whether the function works. So you can see I've got my PK parameters in here, and then I've got all of my PD parameters in here. So you've got, you know, our slope of our drug effect. I've got my mean transit time, baseline neutrophil count, and that exponent associated with the feedback process. So I've got a set of values for those in here. Now again, when I write functions that are done with the BUGS model library, the parameters are going to get passed as a vector. So I have to create such a vector, and that's what I'm doing right here for both the PK and the PD parameters here. Again, you can ignore the statements, like those are, again, came from a more complete model here. In this case, we're just putting in our fixed values. So you can see here where for my PK parameters, I took those PK parameters we just defined at the bottom and assigned them to elements of our theta vector. And I do the same for the PD components here. So you can see we've gone from 1 to 9 here. And then I filled it in with our F's and our T-lags to fill out our theta vector in here. And down here I finally do a call then to our new model. Now the other thing I need to do is somehow get all these other components for time, amount, rate, etc. And you can do that in a couple of ways. If you want, you could actually hard code those right in the model. I often find it easier, however, to do those is to write those up as like a sort of a pseudo data file here. So if we scroll down, you'll see I've created such a data file down here. So you can see I put in a bunch of times here going, what do we got? I guess we're going out to 288 hours. I'm trying to remember if this was hours or what units I was using. I think it's hours. Does that make sense? Let's see, 288. I'm trying to remember what that is in days. But anyway, we've got, yeah, that makes sense. That would be 12 days, yes, which is how long we measured the neutrophil counts. So you can see I filled that out that way, and then I've got corresponding values to include a dosing component in here. So you can see we've got what an 80 milligram dose in here. We've got our multiple dosing regimens, so the drug's given every 12 hours, so we've got an II in there, and so on. So it's basically like a non-mem style data set in here. And I guess I've got, 14 doses and so on. So we've got our dosing regimen built in, and pretty much everything else is a bunch of zeros. And we don't have any dependent variable here because we don't need it. We're just going to test our function by simulation. Let's see, and the only other elements, so this is going to give, this x hat will contain all of the amounts for all of the compartments. Down here I also then generate the concentration in the central compartment and our neutrophil counts in here. Now recall that all of the amounts, or whatever we want to call them, for our various components, the ones for the PD side of the model were all changed from baseline, in other words changed from circ 0 in here. So when I do the calculation of the actual neutrophil count, I have to remember that this amount in compartment 8 is actually a change from baseline value for our neutrophil counts. So if I actually want the neutrophil counts itself, I have to add back in the baseline value, which in this case corresponds to theta 7, which is, you can see right up here, that's our baseline value. By the way, I probably mentioned this before, but just in case it didn't come out, the theta, I by habit I've tended to use the name theta for the vector I pass. It doesn't have to be theta. You can choose whatever name you prefer for that, so it's not a reserved name. Okay, I think that's all the pieces in order to do such a simulation. And we're just going to do it very simply, just using the GUI here from our black box. So I'm going to go to Model and pick Specifications. We're going through the same process we did back in our first hands-on example near the beginning of the course. Let's highlight the word Model. Hit Check Model. It says Model is syntactically correct, so far so good. One of the more common things you might get when you're working with BUGSModelLibrary is, I forget the exact wording, but it may say something like unrecognized logical node, and when it does so, you might find the cursor pointing, like blinking over here, like right next to the BUGSModelLibrary model that you tried to define. That means that you must have done something wrong, either in terms of defining that model or in making the appropriate connections, because for some reason WinBUGS isn't recognizing the name. It could be something as simple as a misspelling anywhere along the line, or it could be something more complicated than that. But at that point, that's what it's indicating. That's also the message. If we had tried to use this function in the same black box session in which we compiled the model, we'd get that kind of an error too, because it actually would not yet have been defined for that session. Okay, but anyway, it worked fine here. It says model is syntactically correct. Let's scroll on down to our data set here. Highlight list and hit load data. It says data loaded, so apparently we're okay there. There's not like some undefined variables that inside of that data set. And then I hit compile. Okay, and at this point there's no random variables, so there's no initial values that need to be loaded. We've got a model all set. It's a completely deterministic model, in fact. So the way I approach this usually is I go back to Model, pick Update, change the number of updates just to 1. Go ahead and hit Update, and that should go through and calculate one set of values then for our, for things like your X hat and for C hat and Newt hat here. And to look at those, go up to Info, select Node Info. Open that and you get another little window here, and then give the name of the thing whose values you want to look at. So for example, we can look at the entire collection, say X hat. I could look at the entire collection of amounts for all the compartments. So I'll hit values there, Let's widen this so we can actually see it. Takes a minute because there's a bunch of them. Because remember, there's going to be for each time point there's going to be 8 values. Okay, so you can scroll back and look at that. Remember that for what is it, compartments 4 through 8, those are changed from baseline, so don't be surprised by the fact that you see negative values for that. And you can see we've got several negative values all interspersed in there. Now it might be easier to sort of interpret this if we go and put in, instead of all of those, let's look at some specific things like our like the plasma concentrations for the drug. Did we get the PK right? So I think I called that C hat, didn't I? We'll find out. Okay. So you can see it's generated values for that. Of course, you have to make sense of what times those are at. And unfortunately, I don't think, let me double check, but because these are not random variables, I don't think it's going to let me do any plots. Let's just double check that, but I think we can. So for example, if I try to put C hat here and everything stays grayed out. What did I call time? Just time? I think so. Yeah, it won't let me plot that. So if you actually want to plot your simulations, the best thing to do would be to tie this in to an R program. The other trick you can do, if you really do want to take advantage of that, is actually put some random variation somewhere in your model. So in fact, why don't we do that as an illustration? Oh, that's not the button I wanted to hit. There we go. Okay, let's take our model. Yeah, let's throw in a, where shall we put it here? Let's just throw in some random variation in here just to create a sort of a false random variable in here. So for example, here we could say something like CONC here, I, and let's make that, I don't know, let's make it real trivially simple. Let's just throw in a little normal, just a small amount of normal variation in it. Okay, and I don't know, what do we want here? So if we want maybe like, let's make it like 5% random variation in here. Oh, that's right, I'm not doing this as a log normal, am I? That makes it slightly messier. I forget what the scale of values was. I don't remember. Let's just put a small number here then, because any small number will work here. Oh, actually, I forget, this is a precision, so a small standard deviation will be a large value of that. Let's see, 100. Oh, I don't know, let's even make it a little bigger here and there, and we'll do sort of the same thing here for our neutrophils. Up, and I see a mistake I made already up on top, though. That needs to be a squiggle. And we'll do the same thing, NEUT hats. And just put a fairly large precision on that. And so if you actually wanted to be able to do plots, this would allow you to do that. So let's go back up to the top. We have to go through the process of compiling it again. Okay, I misspelled something. What did I do here? Oh, too used to using R here. It needs to be D norm, not R norm. Okay, now we're okay. Let's get our data again. Okay. Let's do our gen inits, and okay, let's go ahead and do 1,000 updates this time. If you guys can give me a second here, I need to go quickly attend to something. It should take me only a minute here. Okay, sorry to abandon you there for a moment, but I'm back. Okay, anyway, we can go ahead and do that. Did I run it? Yes, I did. The updates are finished. So now we actually can look at plots if you want. Okay, what do I want? I want inference, compare. So I can put in, let's see, what do I want? For the node, I want, here, let's go ahead, for example, we can look at our concentrations. So I could say const for that. And our axis would be time. And okay, what went wrong? Well, that just confused me, because that one should be a random variable. Let's try that one more time. Yeah. Okay, well, that's got me puzzled. I expected that not to give me any trouble at all. Let's see when I put in the other one here. Huh. Okay, well, that's very strange. Oh, I know exactly what the problem is. I just did a silly. Okay, because I pointed that out to you before. If you want to do stuff like that, you have to monitor those things. So we needed to actually list it as a monitored value. So I need to monitor it by setting that for const and for any UT. Okay, now let's do another update. Okay, I did that. Now there we go. Okay, so let's do our concentrations first, since that's more of a familiar thing to us, I think. So you can see there a plot here, because we put such a high precision around that. You see, you can't hardly distinguish the variability on it, which is fine, because what we wanted to know is not about the variability. We wanted to know whether we seem to be getting appropriate results from the differential equation solver. Of course, you'd have to compare it to something else to know whether the magnitude is right, but certainly we have the right basic relationships here. We've got our two I included the sampling schedule like the one that I told you that was used in the study. So you see the two quick spikes at the beginning, and you see the last one for the last dose here. And if we do the same thing then for our neutrophils, you get a picture then that looks like this. Oops. Recall I had put in only one dose level. It was the highest one, or the 80 milligrams. And you actually do see a pattern similar to what you saw in the data here, where it starts out at some baseline and then drops. So even though the dosing stopped back at, let's see, the dosing was what, for 7 days. So I don't know, do your quick math there on what 7 times 24 is, but that's back here somewhere. There's still a continuing drop here because of the lag associated with the life cycle of the neutrophils. So the model actually would eventually recover, but that would be out here at some later time. So anyway, the point of that exercise here was just to show you the notion here of how to actually begin to test your functions to see if they're working. If you really want to know if the numbers themselves are correct, you're pretty much left with having to solve your model in some other framework. So for example, you could write it out in R, or if you're more used to using something like adapt or WinNonlin or something like that, you could code it in one of those and do a quick simulation just to confirm that you got the same numbers using this as you do with some other tool that perhaps you're more familiar with. So that's pretty much what I wanted to cover today, is to sort of show you that process of, one, how to build the model, and two, how to just test the basic component Pascal function that you've written. I guess this is a good point to sort of stop and see if there's any questions, and give that a couple of minutes here, and if not, we'll close out for the day. And I guess while I'm waiting to see if there are any, just remind you that next week there won't be any classes, so we won't meet again until the Monday after that. And we'll continue on with our topics at that point. The exercise here for hands-on 4, I'm assuming, is going over both weeks, or actually I guess you have 3 weeks in a sense, since I won't be around next week. That's also assuming you're not as busy as I am dealing with family. It's also a time I guess you could work on the course project. See, so far nothing's popping up. I will mention, Yiming, I didn't actually comment on the question you posed there about the week's lecture, and yeah, I was tardy about transferring it over to our Connecticut site, where Joe will be uploading it to the site, but I'm imagining he'll probably get it up sometime today or possibly tomorrow, because it's now over at the Connecticut site, but the delay was my fault. Okay, well, I guess I'll say goodbye then. For those of you that are celebrated here, have a happy Thanksgiving, and catch you again in I guess about a week and a half. Bye for now.